Good morning, everyone. All of you in here. Make it sound bigger for everybody at home. Like everybody's in here. Gonna go over Project 5 today and talk about some of the particulars of it. Hopefully, everybody's at least looked over the rules or looked over the specifications some. I know yesterday I spent about an hour just reading it and still wasn't completely sure. Couldn't remember what I did a year ago. It's kind of crazy. All the time you spend on that, and then it just kind of eventually goes away. But I found Adam's video that he did for Spring 16 pretty helpful too. I will hit most of the highlights of that, but if you want just a little different way to say it, he does it a little differently. That's another good resource to check out. You can get to that by changing F16 to S16, and you can get to anything pretty much from the spring semester. So this project is really just about translating. It's really just about taking input in that kind of looks like the programming language we worked with on Project 4, and turning it into something that can execute in our running environment, if you will. It's like coding to an API. So you're coding to this standard that is set by the other code. You can't change compiler.c or compiler.h. The submission site won't use those files. It'll use the files that are on there. Now, one of the tricks, or one of the things I would suggest doing, is pulling those down and then making a copy of them and pulling those into your project to work with so that you can change them, add print statements to them, do all that stuff, but then bring over the pristine ones before you try to submit to the server or when you're running your actual testing and not debugging anymore, so that you know it works with the actual version. You didn't inadvertently change something in the compiler.c or compiler.h's. But that's definitely what I did when I was debugging. Was I would put print statements in there just to kind of see what stuff was doing and to understand it better. The main key to this project is understanding compile.c and compile.h and just programming to what that is. So basically what we're doing, this will be what you write is what we're calling the compiler, and then the resulting output will be fed into the execution part down here. So you generate this structure data, and this data structure is then input into the execution portion. And we'll go over this. I've got an actual example with where we can walk through kind of how it works. It's actually, the first one's the first test case. And then I'll show you some code that actually is how all this kind of works and fits together. And it's hacked. I mean, it's basically, I'm not reading input or taking input, which you guys will have to do, but it's just kind of showing you how the data structures will work and how they'll execute. These are just kind of the different areas. So the grammar itself is really simplified compared to Project 4. Some of the main things that you'll notice is that we no longer have there's no type section. There are no types. Effectively, all the variables are integers, which is much easier than having characters or anything else to worry about. All we have to worry about are integers. All variables, there are no implied types. I'm sorry, there are no implied variables. All the variables have to be defined in the variable section. You fortunately don't have to worry about syntax errors on this. So it says in there that everything will be well formed and there won't be syntax errors in the test cases. But so you'll have this bar section where you will set up your variables, and then you will have the body section. You will parse the input real similar to the last project. Somebody asked me if I used my code from Project 4 for 5, and I think I did. And then I think I ended up throwing it away and just kind of doing it more to what it needed, because it was kind of like trying to fit a circle into a square hole. And so it just didn't work that well. Maybe that was just because of the way I designed Project 4. So it might work for you guys. I don't know. I would definitely probably copy and paste a bunch of the code, especially from like how the print worked. But what was your question?
So I use speak spec function in Project 4.
The which one?
Speak spec. I mean, in Project 4, the video process has some function to use it, right?
Yeah. So the get token and all that stuff to bring the input in is actually in compiler.c. So you don't have to worry about that. So you still have all the get token functionality. It all works. It all works for this language, so you don't have to worry about any of that. And you can definitely copy stuff from Project 4. That's not a problem. And bring in, if you wanted to bring in your functions and try them or use them, that would be totally fine. The basics, though, are that, so once you get into this body section, it starts with an L brace, ends with a right brace, so you got the curly braces on either side, top and bottom, and then you got basically a list of statements. Each statement can be an assign statement, a print statement, a while statement, an if statement, or a switch statement. A couple interesting things to note that make it a little more complicated is that you have a statement list, and then a statement. The while statement and if statement and switch statements have a body. So there's a body for that, a body for that, and a body for the case statement. So they're recursive, or they can one within the other, within the other, within the other, and you have to deal with that use case. I don't think it's that bad once you kind of get the basic structure there. It'll kind of fit. You could handle it a number of different ways, but that is something you have to be aware of with when you're pointing back to certain pieces of code, that where you're coming up and where you're not. Most of the other stuff is just pretty standard programming. You have an if with a condition and a body for the ifs. Notice that all of these guys, so for if, it's all uppercase. For while, it's all uppercase. For switch and case, all uppercase. And then, but for some reason, print is actually not all uppercase. It's, when we look down here, see the while is uppercase, if is uppercase, switch, case, all uppercase, but for some reason, print's all lowercase. Just kind of something to notice. Let's see what else did I miss. Yeah, if you have integer division, so you divide one integer by another integer, the result is an integer, not a float or anything like that. No semicolon after the if statement. Good to know. So, yeah, here, because it ends with a body, which is going to end with a curly brace, so that's kind of normal too. Oh, interesting. So there's only an ID list. There's no variable declaration list. What does this mean? I didn't notice this earlier, but it basically means that, if we look at it, so an ID list is comma separated. So if you have multiple variables, it's going to be I, comma j, comma z, comma x, comma y, semicolon. So no, there will only be one semicolon in the variable declaration section, and you'll just parse through those. We already talked about that, so we're good. So the execution semantics, these guys all work the same way. I mean, this is a bunch of language talking about how they work the same way that you're used to in every program that you've ever done. I'm not going to spend too much time on it because we'll kind of get into it with the examples that I've got. But, the if statement, you evaluate the condition, you go the true branch or you go the false branch. While statements, while it's true, you keep going. and then if it evaluates to false, you stop. Now, the API that we're programming to for this doesn't have a while statement construct. The structures don't have that. So you have to program it in kind of more like it would be an assembly or assembler, where you do some kind of comparison, and then based on that comparison, you do the code afterwards. You follow through the code, and when you get to the end of it, you go back up above that if statement and do it again until you get a false at the if statement, and it goes out and around. And that's kind of what this is showing you. So you have a label, an if condition, it goes through, and then it goes to label, so it hits this if condition again. If it were to hit else, it would come down to here, and it would exit out. But this goto, we do have a goto construct. Keeps you going like this. Keeps you going back that way till that condition's not true anymore, and then you exit out. But it takes you back up to the label. Just a little different, but that's the API's got some weird things that I'll just kind of expect you guys to figure out. One of the other weird things here is it here? It's not as important here, but no, I'm gonna wait. All right. So that's the while. The switch statements, kind of like just normal switch statements. One of the interesting things to note is, well, this is kind of how they're constructed. So there are multiple ways to build these switch statements. I know that when I did Project 5, I did it a different way than this. But in the video that I watched of Adam's, at least, he said do it this way. The other way gets, I guess, a lot messier and a lot more difficult. And he suggests doing it this way just because it's easier to understand and program, basically. They also have a default capability in the switch, so you can, that's for, if it doesn't hit any of the other cases, it hits that one. The print statement only prints an ID. It only prints a variable. There's no passing in a string. There are no strings. So it's a variable, means it's only going to print numbers. All right. So I'm going to walk through this example, then we're going to go look at the actual some code I put together, see how it executes, and if we have time, we'll come back and do the other example that I have. So the code here, this is actually taken directly, I think, from test 1, the very first test that'll be in your test scripts that you have. And it defines one variable. It sets that variable to 42. Of note, the variable should default to 0. All variables, all integers default to 0 when they're created. And then you print that value. So the output should be 42. So I set up basically a start, which is points to the first structure that we're going to start with for this one, which would be an assignment. So you have two structures that you worry about. And if we look here, the big structure are statement nodes. It contains assignments, prints, if statements, goto statements, and you specify which one of those is in there based on the type. So you set this type value. It's got an enumeration for it that's one of these values. So it can be a no-op statement, a print statement, assign statement, if statement, goto statement. Can somebody tell me what a no-op statement probably is? Yeah, don't do anything. Just go to the next statement. Just no operation. Comes in handy in a couple spots for sure. Surprisingly, it seems kind of simple. So yeah, you build these, and then based on those, it has one of these structures inside of it, which can also link to other structures within it. Now, let's go back to, all right, so for my case, I set up a start, it points to this first statement node, which is of type assign statement. Assign statement points to another guy that's an actual structure called the assignment statement structure. And it's got a left-hand side, an operand 2, and then it's got the type of operation. In this case, we're doing I equals 42. There's no plus, minus, whatever over here, so there's no secondary. There's no operand 2, and we just set it equal to 0, is what I did. I think it actually says that in the comments somewhere. So the left-hand side, value node, name, value equals 42. That's not right. All right. Yeah, these are backwards. I'll make it nice and confusing. And now my animation's all messed up. Okay, so you've got, this is the 42. 42, we don't have, even for literals, you have to create a value node. So 42 is its own value node. Its name doesn't matter. If you want to use it, you could. You don't have to. And then for the value node for the name, it's I, and then we default it to 0. And so the left-hand side is pointing at I. On the right-hand side, the first operand is 42. Operand 2 is pointing to null or nothing, and then we have the offset to 0. These statements here will do the I equals 42. Then we'll come back and we'll go to the next statement. So type print statement. It's got a print statement and a next. Print statement goes to the print statement structure. It only takes an ID. That ID is pointing to that same value node. And then it goes to the next statement and null. So that's kind of the structure of what we feed into the execution engine.
This is basically project 4, but we are doing it ourselves.
Yeah. So it's kind of like Project 4, except you're building to this API instead of building this tree structure. So you can only, it is, I mean, you just use the structures that are there. You can't change them. You can't add to them like you could in Project 4. Compiler.h and compiler.c you cannot change. You will not upload those. Those you have to use the server version. So you have to fit within the structures that are there.
Do we need to create a pass tree? I don't think we need to create a pass tree.
Say that again.
Pass tree, do we need to build?
No,
Right.
not if you don't want to. I mean, maybe if you find it helpful or something. I might build some kind of structure to hold the code itself so that I could refer back to stuff, because there will be some of that where it'd be handy to be able to know how to get back to somewhere or do something, but you could also do it pretty easy with a stack for that, for your program execution, just like it does.
But we need to get tokens, right? So we need to first parse the grammar, parse everything and get the tokens. But in order to get the tokens, we need to create a parse tree.
You don't have to create a parse tree to get the
So
tokens.
just need to put all of these variables in the input into those nodes, right? In this case, we need to append the 42 to I, the node I.
No, it does that. So this statement is an assignment. This object is an assignment. So when it's run and executed, it takes the I and it makes it equal to 42.
So we do not need to change it.
No,
By us.
no, it won't change by you.
Just put it there.
Yeah,
But we need to know whether this statement is an assignment statement or the right statement, right?
yes.
So how do we know that? We have to create a parse tree for that, right? Because we need to parse the grammar to understand whether it's an assignment statement or a right statement.
You need to parse it to know which statement it is, but you know before you add it to a parse tree what kind of statement it is, right?
Yeah.
You know by those, if you were doing something close to a recursion descent parser, then you would know that, okay, I've got an assignment statement here because there's an equals. And so I look at this one, I look at this one, and I put all that stuff into that assignment statement.
directly start building that data structure.
Yeah, you're building this data structure here. So what we have here is exactly what you're trying to build.
Are we implementing the arrows, sort of?
Do what?
Like the arrows, like connecting the dots?
Yeah, the arrows too, because the arrows are pointing to these other structures. So we'll look at some code. This is not how your program will look. What this is imagine that the only input I needed to handle was what we just saw, was those 4 statements or 3 statements. So I wrote a program that basically builds all these structures real quick and dirty just in one line, one set of, in one function. And then I submit it so you could see how it actually runs and we can kind of talk about it. Yeah. What's not? Oh. We can try. You made me the move. Is that any better? I mean, I can try to play with these, but these blinds are about had it. That's good? Okay. I could make it a little bigger. It's okay? A little bit bigger? I can do that. Better or more? All right. So these are not created necessarily. I tried to give some order to how I was creating the variables, and I ran out of time, basically. I wanted to make the pretty diagram for everybody instead. But so these don't have any kind of smart order necessarily. But I started out, I created the I variable, so the I value node. I just created it first, which is probably similar to what you want to do. Might want to take all those, create the value nodes, and maybe stick them in some kind of table so that you can look them up. Whenever you want to refer to the I variable, you see the I variable, you have that token. For whatever variable it is, you have that token, you could go look it up somewhere, kind of like you had to do with your symbol lookups before. But you want to keep track of where this variable is in memory. So you'd want to keep track of the pointer, basically, to the value node. And then, so I initialize the value to 0, and I copy in, for the name of it, it's the variable I, so I copy in that name. And then I build a literal. I don't worry about the variable name or anything. And then we start building the assign statement. So we'll just do some of this as I go. So the assign statement is going to have, if we look back, it's going to have the left-hand side is pointing to that I var, and the right-hand side, the first operand, is pointing to the value of 42. So if we look, I've got the I var for the left-hand side, and then the literal variable is operand 1. Then we start. I go ahead and set the start statement node. So the start statement node, I set that the type equal to assign statement, and then I make the assign statement variable inside of there equal to the assign statement I just created. So if we look back here again, we see under assign statement, the assign statement's pointing at the assign stmt is pointing at assign statement, the assign statement structure, which is the one that we just built. All right. So we set that to start, which is my starting place, and set the assign statement. Now I need to build what it's going to point to as its next. So to start, if we look at the statement node, it's got a next, that points to it's something of its type. So that can be set to null, but it can also be set to the next statement. So we're going to build the next statement node, which is a print statement, which just needs the ID set, and we set it to that same, pointing to that same value node. And then we set for that second statement, we set the print statement pn, we set the type equal to print statement, and we set its next equal to null, which signals that it's the end of the program. And then start next, so that we set up, we move this statement so that start, after it's done, goes to the next one. And then we return that value. So, a couple points here. This is the function that you're implementing. This is the function that interacts with the API. You don't create a main. The main function already exists. In fact, you'd get an error if you tried to compile. The main function already exists over here. So this is compiler.c. It's already got a main function, and it calls this, that parse generate function, which returns a program, and then it executes that program, which is actually this function right here. We'll go over that in a second. Going back to compiler.h, it's got an entry for parse generate, so it's got a prototype here for that, and that's what you implement in your code. So you will include the compiler.h. It's already included in compiler.c, but you'll include it in your code to link everything up. Does that make sense? Some notes for you guys you may want to check out. Like I said, you want to be very familiar with kind of how these are working. Now compiler.c. So we start out, our first statement node is an assign statement, right? So that means its type is assign statement. So when we come in, it's not equal to null. This will keep going until it's equal to null. That's why we had a null at the end. And then we're going to look at the type of that statement. And in our case, it's an assigned statement. So they're nice enough, and they check all these null values to make sure that if, like, for example, your op's not equal to 0, if your op's not equal to 0, then the second operand shouldn't be null. So they do some null checks and some validation in here and give you some helpful errors. So once we're in this assign statement, we've got 4 different kinds of possibilities. 5, actually. So the case of 0 is the one that we're worried about. We set the op equal to 0. So it's going to basically set op1 equal to PC and then take this result and put it into, and take op1 and put it in there. So this is doing the math part. And then this part's doing the rest. It's taking our program counter, or PC, which is the current instruction that we're executing. It goes to its assign statement, the left-hand side, and it sets that value equal to the result. Since that value is a pointer, it's pointing back to wherever value node is. It just works. So we're doing next. It grabs the next statement. So in this case, that would be a print statement. So it breaks out of the case, out of the switch, comes back to the while, comes back through. PC type is now print statement. So it's this guy, does some validation checks, does this simple print statement, and then goes to the next statement again. So let's execute this real quick, and you guys can see, in theory, if it works, we will end up with 42 is the output. That's all the output you should have. That's the only thing that program that you parsed outputs. So that's all you should have. 42. Kind of makes sense? A little bit? Cool. Couple other interesting little gotchas on this thing. So the condition operator has to be one of these values. That's the semantics of how the grammar works and how this API works. That means you can't pass in, there's no double equals, there's no equivalent to, right? Just have greater, less, not equal. So no double equals. Where is that going to cause us? May not be obvious. It's going to cause us a problem somewhere. Particularly on let me see. So we have a case statement, switch, case, blah, blah, blah. Here, how is this implemented here? Yeah, but we have no way to do an if statement with equals in the API.
Boolean.
No Booleans. We have greater than, less than, not equal to. So let's look at the if construct really quick. That's inside the API. It has a true branch and a false branch. How can that help us?
If we are having greater than, less than, or not equal to a valid statement, then it goes to true. Else, if nothing is valid, then it goes to false.
Right. So what I think I hear you saying is if we have a not equal to, if A is not equal to B, the else is an equal. Right? So that's kind of your trick there to get around not having that, just to make it a little more, and that's not uncommon with APIs. They have certain things that, you know, the coders didn't think about when they wrote them or whatever, and they're 15 years old and now you're still using it, and you still kind of have to fit to whatever they have. For you guys, mostly it's just to make this a little more difficult, but also not too hideous. But yeah, that's for the switch statements, that's your little trick. That's the little trick that they'll have, is that you have no way to do the equals. One of the other things that I don't remember why. I don't remember the subtle nuance of why right now. But the execution part, the execution function for a go-to statement, so it'll go to another spot. It doesn't do a go to next. It doesn't do PC equal PC next like all the other ones do. When you're exiting out of them, if you look at, or maybe it was this one. Actually, it might be the if statement that got me with that one. It's one of these two. See how this one has a PC go to the next, so it kind of makes you to the next statement. But if statements don't have that, and neither do go-to statements. So that's something to pay attention, just to kind of put in the back of your mind when you're working through some of these, that might be an issue with how you build kind of how you're building your structures for each of these. Questions? All right. Let's try to get through a little bit of the second example. All right. So in this example, we've got a while loop. We do a print, and then we increment. So what is, I will be defaulted to 0, right? So I will be less than 5 to start with. It'll run this while loop. It'll do a print. It'll increment, and then it'll keep doing that, hopefully, for a few times, and then it'll exit out and go to this print. Now, this code, the way it'll kind of look just at a pseudocode level, this is what it kind of looks like. You have this label that's above if, that's where we're going to go back to. If I is less than 5, then print I plus 1, go to above if, it goes to here, does that several times, and then it kicks out, hits the else basically, or the false, and then goes to here. That's not quite how the specification says you should build it. It doesn't, the false branch doesn't go to here necessarily. It works a little differently than that. And you can try to make the false branch go to that point, or you can do it like the picture does and have it work. I remember not doing that the right way and struggling with that a little bit. So now we're going to build this guy. It's a little more complicated than the last one. Start with start again. Statement node type equals if statement. So that's building this first guy right here. And then the if statement has a condition operand 1, a condition operand, that should be 2. Somebody used copy and paste. Then it has a condition op, so the type of condition operation, which can be less, greater, or not equal. A false branch and a true branch. So the condition operand is going to point to this variable I. The second condition operand is going to point to 5. So it'll compare those two and see if I is less than 5. Then the true branch, if that's true, is going to go to the next statement node. So see how this is creating kind of a little set of statements within that one statement? So you kind of have this tree almost that's going down. So this statement, the print statement, is going to have a print statement with the ID passed in just like the last one, and then that's pointing back to that I bar. Or the I value node, or I, or whatever you want. Once it's done with that, there's another next statement. This one's an assigned statement. So this is a statement node pointing at an assigned statement. It's got a left-hand side just like the last one, except this case, the operand is a plus. So the left-hand side and the operand, the first one, are pointing back at I node. That's because we have I equals I. Then we have a plus, operand 2. Which is just a new value node sitting out there. It's literal. Now, once we get done with this statement, with this next, where do we go next? Based on the code. Yeah, go back to so the next statement in here it must be a statement node. It can't be a particular statement. So it's going to point all the way back to here. Now we want to talk about the false branch. So the false branch is going to point to a no-op. I don't remember specifically why we use the no-op for this. I know it has to do with everything just kind of lining up better when you do this, and it makes it, I think it'll make your life easier. This is exactly what the specification says. For the while, you come in, you have this if statement, you go to the if node, the false branch goes to a no-op statement. And then goes on from there. But that gives you a good launching point for the next from here and for the false branch, and then keeps everything kind of in there, and it has a symmetry to it. It's nice. It doesn't really cost you that much. So the no-op statement is pointed to also by the next. So this statement node, once it's done and consumed that, it also is going to go to here. So once there aren't any more of these, once it's done, if there was nothing there, it points to there, and then the false branch points to there too. And then the no-op points to a print statement, which is this last print statement here, and we're just kind of going on about our way. ID points back to the same, has a pointer back to the same value node, and then we're pointing to null. That'll terminate. There's a relatively straightforward while loop.
How do we refer the value again? So let's just say we are doing a get token. We are at a print statement.
Yeah.
And then we are again at the assignment statement. So we have to refer I again. We have to increment the I again, right?
Yep.
So I have to save I somewhere.
I is, well, the value node I is saved right here.
But I have to know that there's a value node, because if I don't create a parse tree, then if I just do a get token, let's just say I'm doing get token and the next value is I, and it's an assignment. So how do I, so then I have to search the tree again to find the value of I, right?
Well, what did you do in project 4?
I just went through the parse tree, I just followed the parse tree.
So every time you needed a variable, every time you had to refer back to a variable, you went back through the
No,
parse
that
tree?
was recursively done automatically. So let's just say if A was equal to 5, then I used to travel a parse tree. So while creating the parse tree, I used to save everything in a variable.
Yeah, exactly. Saved everything in a variable, right? So in this case, wouldn't maybe you have a variable?
So basically, it's like a hash map of.
That would be an awesome way to do it, I think. Not the only way. I mean, if you put it in a hash map, you wouldn't even technically probably need that name field of value node. And you could just use that for the hash map. It would work. That would work really nice, I think. But I'd have all my variables in there. And then when I need one, it has the pointer. It knows what the pointer is to the value node wherever it is on the heap.
Oh, so hash map with a pointer, the value is a pointer to the node.
To the value node.
Oh.
Right? Because it would have to be. I mean, that's what you're worried about are the address locations of this stuff. And so that way you can pass it all in. You don't have to worry about keeping track of the value of I.
That would be done in the
It'll be done as the program executes. So that brings up an interesting point. Do you want to, let's look at my code again. What does this new keyword do when I'm doing C++? Allocates memory to where? Yeah, so you're technically supposed to deallocate it. We won't talk about if I'm doing that or not. It's a really short program, so I wasn't that worried about it. But yeah, I should be means I should be deallocating it too, or deleting it. But
in C++, it will do automatically.
it will, but where does it put it? Does it put it on the stack or the heap? When it does automatic. The stack. The reason I know is because I wrote this without the new keywords to start with. And it doesn't work because you lose all that memory. The stack is there and it puts it all on the stack, and then there's a return. There's a return at the end. What does a return do? It takes EVP, or it takes ESP, it moves it back up to EVP, and then it does the couple pops, and then you're back in the prior function frame. So all that memory down there that I created was gone. So yeah, you have to do the heap, and this, by returning this pointer value, you're still pointing at a heap location that's pointing at all the other heap locations. All right. So yeah, that's another fun place to get stuck. So this code here, it's actually not working. It's running, it's just not doing exactly what it's supposed to do. So this is my simple implementation of the while loop, and I just didn't have quite enough time to get it tweaked working completely, but it's close, so we'll at least look at it. You've got some value nodes. I set the 5 value, the 1 value node, and then this ivar. So the ivar could easily, like you were saying, go in a hash map instead of being a separate variable like I'm using here. I have the benefit of only having to worry about this one coding problem and not infinite number of coding problems like you guys do. So then I this does a print first. So it does the print statement, and then, the statement node, print node, we have start, Start should actually go, yeah, start goes to an if statement. So we can see that down there. And that's the first statement that I build up here with the I bar, the 5 val, less, and then the while statement, body node, which I create down here. It's of type, first statement's of type print statement. And I just refer back up to the print statement that I built up here. Print node. And then the next is going to be an assignment node, which I define the rest of right here. What did I do? Define the rest of right there. And then one of the other, so, oh, I forgot to put that in my chart, actually. Didn't I? This has to be, it has to be a go-to statement. I just forgot to put it in there. So set the start, and then I create the go-to statement, and then go back, and then return it. So if we watch this run real quick, because we're almost out of time, it does the 0 through 4. It's not doing the last print statement. I just don't have it in there yet. Otherwise, it's working. But that is actually a common problem with this one, is that getting those subsequent statements, so getting the program execution back to that, that set of prior statements without just exiting. And that's the bug I'm stuck at right this second. But it's really close to what you want. And it gives you a rough idea of what all these kind of look like when it's working and what you're going to be kind of building dynamically. Other questions? What's that? Yeah, the picture? Sure. Not from there.
So the go-to statement will go back to the if statement.
Yes.
But here is go to start node. Because the start node, I think the start node contains not only the while statement but also the break statement.
It does. The start in the code, the start statement was pointing at the if statement. It just looked, because the layout was kind of wonky.
Yeah, I think that's because we need to check if I less than 5. If I doesn't less than 5, then we should go to the while statement, not the whole body of this.
To the while statement, if what?
I mean, the go to statement meant, I think we should go to the while statement, not the whole body of this command, of this input.
Yeah, yeah. So what I believe should happen is the go-to, statement will go back to, it does go back to the statement node. But it's the go-to statement, that's what I'm missing. So the statement node, type go-to statement, and then goes to target.
There is no while statement. There is only if. So basically, this statement node is the if. Is the while statement. Yeah. So it has to go to the while line, not to the if.
Yeah, it has to go, well, there is no while statement, so it has to go back above the if. Just like it was saying, up here. See, this is while, condition, list of statements. So we imagine there's a label set there. We do if condition, statement list, go to label, goes back up to here. Same thing.
Okay, got it.
Kind of like, that's what I was trying to get at on this slide was that you were going to, if I is less than 5, print I equals I plus 1, go to above if, so that it goes through that loop.
One question.
Yeah.
If I use a hash map, and if there's a variable I inside a scope of I, all the variables are defined.
There's no scoping to worry about with the variables. They are all defined globally by the way this is defined. They all have to be defined in that variable section. So you don't have to worry. So you can have a global hash map, basically. Other questions?
Do you have to pass the test cases from the SID in order to get full credit, or do you still have to pass test cases from the servers?
Just like all the other ones. Test cases on the server or what matter.
We need to store the value of each variable in our own list.
Something. Yeah, that's what he was talking about with the hash map. Either a hash map or a linked list. I mean, anything works. Just some kind of table lookup, some kind of lookup, so that you can find the variables when you need them to make it equal to that value node, so that you use the same address space for the same variable. So last thing, and I'll let you guys go. I'm already over by a minute. So you have these bonus options. If you didn't do that well on Project 3, you can resubmit, but if you did better than 70% on Project 3, that would be a total waste. The same for Project 4, so you can resubmit. This is for people pretty much that got below 70 or got a 0 and want to work on that and spend the time, and it's worth it. If none of that appeals to you, you can replace your lowest grade between those two projects by doing this other project that you came up with. This one gives you full credit, so if you want to do a full credit replacement and you're not worried about just getting a 70, this gives you another option if for some reason Project 3 or Project 4 didn't go as well as you wanted. So
is that an extension from this project, or
it is. So the one that's of full value is an extension from this project, and it's basically just implementing arrays. So it's adding the array capability. We add in this lbrac, right, rbrac. It, at first blush, without really digging into it, doesn't seem horrendous, but there's some interesting things there. And he wouldn't be giving you 100% credit for it if it was, just trivially easy, but I think if you mapped it out and just kind of thought through it, if you finish 5 and you get 5 done, then, that's, if I needed the points, that's the route I would probably go. But
when are the bonuses due?
Everything's due all at the same time. I think the 4th. And that'd be right. All right.
We have a midterm next week.
Yep. Midterm next week, I believe on the 21st, which is Monday.
But we didn't have midterm